Hello, this is How to Encode LEB 128. Unsigned little endian base 128 allows you to store small numbers in a single byte and allows you to store increasingly larger numbers by setting the high bit and adding additional bytes. For my example, I picked a number at random, 71,397. Here it is in binary. Begin by copying the lowest 7 bits to a byte. Right shift the number 7 places. If your programming language has unsigned integers, this is probably done by a logical right shift. The bits at the right side will just fall off the table and then be filled in on the left with zeros. After right shifting, the number is now 557. And this number is greater than 0, so that means that it will take more than 1 byte to encode this number. Set the high bit to 1. Copy 7 bits from the number again. Right shift the number 7 places. And then the number is now 4. This is greater than 0, so need to keep going. Set the high bit to 1. Grab the lowest 7 bits. Copy them to a byte. Right shift 7 places. And it's 0. We're done. This is a function I wrote in the C programming language that does that. In the simplest case, where it only takes 1 byte to store the number, it'll just simply skip over that while loop. So the number 127 is a number where the lowest 7 bits are all 1, and when you bitwise AND it with a number, the positions where the bits are 1 in both numbers, they will be set to 1, and if one or neither of them are 1, then they will be set to 0. Then right shift the number 7 places. This is the right shift operator in the C programming language. And then, like I said, if it's done, we'll just skip right over the while loop, print out the value in hexadecimal followed by a new line. If it's going to take more than 1 byte, then jumps into the while loop. I add 128 because that is the value of the bit in the high position of the byte. Print the value in hexadecimal. Grab the next 7 bits, right shift 7 places, and then see if you're done. Repeat it until it's done. Here is what the code looks like using a do while loop, in case you think that you can't have the same 2 lines of code twice because you're wasting lines of code. And I think it's a little bit more confusing, and it's about the same size, so I like the one on the left. And then arithmetic right shift. This works a little bit differently than the logical right shift. Instead of just filling it in with zeros, it just fills it in with the sign bits on the left side there. And that's so when you right shift a negative number, you don't just get a big huge positive number and not know why. Signed LEB 128. Encoding of a signed LEB 128 integer is somewhat similar to encoding an unsigned LEB 128. With arithmetic right shift for signed integers, we are still pulling bits until we have extracted all the ones with positive integers. With negative integers, it's more like pulling bits until we extract all the zeros. There is an additional check that needs to be made to make sure the highest bit used from the number is the sign bit, and in some cases may need to add an extra byte of padding to make sure the bit read as the sign bit by the LEB 128 decoder matches the sign of the number. This is the number I picked, negative 8,839. I picked this number because it's a negative number and because the last bit that's grabbed is going to be a 0, and that's not the sign bit. Copy the lowest 7 bits to a byte. Right shift 7 places. Notice that since this is an arithmetic right shift, instead of it just being filled in with zeros, it's filled in with whatever was the highest bit when the right shift happened. After the right shift, the value of the number is negative 70. Since this number began its life as a negative number, when we're done, all of the bits will be ones, and the value of an integer with all 1 bits is negative 1. So since this is not negative 1, set the high bit, grab 7 bits from the number, copy it to a byte. Now, the value is negative 1. However, this is the high bit of the last 7 bits grabbed from the number. This is usually the sign bit, but sometimes that last 0 lands in the spot. The LEB 128 decoder is going to look at this bit to determine the sign of the number. So we have no choice but to grab another 7 bits and add another byte to our output. Set the high bit to 1, copy 7 bits. As you can see, that bit right there is 1, and it's the correct sign bit in this case. So the condition to exit out of the loop for unsigned LEB 128 is pretty simple. If the number is 0, you're done and you can just move on. With a signed 128 LEB number, you need to check that bit to see if you need to grab another 7 bits for padding. You can bitwise AND it with the number 64 because the number 64 is a 1 bit in that position, and it will give you a number either 0 or 64, 0 being a positive sign bit, 64 being a negative sign bit, and you just have to check that every single time just to make sure you're doing it right. Here is where I've taken that first example and extended it to add the extra step of checking the sign bit. And this kind of looks a little silly to me. If the number is 0, then it started its life as a positive number. Then when you're finished, the sign bit should be 0. If the number is negative 1, it started its life as a negative number, and the sign bit should be 1. Here's where I've taken the do while example, and I've extended it to do the same thing. I like this a lot better. All I did was just change the test and put it into a function.